Hi, Amy. How are you doing?
I'm good, thank you. How are you?
Good, good. So, how do you find calculus now?
Yeah, all right.
All right.
Um, yeah, just doing a bit of the stuff from my book, and
Okay.
yeah, just getting through it. It's a lot.
Yes. So, how do you find while you're answering questions from your book?
I think I'm glad I waited
Mhm.
because now I got obviously a bit more knowledge in things. I
Yes.
won't keep stopping and starting and like that.
Okay.
So yeah, it's good.
So, easily, are you able to answer most of the questions in the book?
Yeah, so
That's
far I
good.
haven't come up with any issues,
Oh,
but when
that's
I
so
do, I'll
great.
send you. Yeah,
So, whenever you have any difficulty, just post me those questions.
yeah.
That will mean that I might have missed few points, right? So, we can cover up for those. What I realize is that we had introduced to you this concept of chain rule, correct?
Mhm.
And now the next chapter is the rate of change, which is kind of related with change rule, uh, chain rule. So we'll take up few questions which are application questions on rate of change. Okay. So till
Okay.
now we were only differentiating with respect to x. Like y equal is a function of x, and we differentiated with respect to x. Now we'll see how to differentiate it with respect to time or radius or some other parameters, right? And there, of course, we are going to use the chain rule. Okay. So
Okay.
let me share with you the screen, and then we'll go from there. So you can see my screen, right?
Yep.
Good. So it is related rates problem solving strategy, which is what we are going to study today. One of the most important topics in calculus. Most of the applications which you see are of related rates, which are being solved by using the techniques which we have learned. And normally in life, when you see time is a big factor, right? So
Yeah.
we have to see how changes are happening with respect to time. But when you work on few things, for example, if you pour liquid in some vessel, then you want to relate the change in volume and change in height and things like that. Correct?
Yeah.
If there is an oil spill, then you want to relate how what the radius of the oil, how the area is changing, right? And how it is affecting the wildlife, right?
Yeah.
So all these factors we see that we are covering rate of change with respect to some parameter or the other, and this parameter could be time, could be radius, could be volume, could be height, or anything. Correct?
Yeah.
So the function which we worked with was y equals to f of x, where f is a function of x, but x could be anything, correct? X is a variable, correct? So
Mm.
keeping that in mind, we'll work out some examples today. So can you read these few points which I have mentioned right in the beginning about related rates problem solving strategies?
Yeah. So in related rates applications, rate of change of one quantity is given, and we are interested in finding the rate of change of a related quantity.
Correct.
So first step to solve these problems is to identify what is given, what can be derived, and what is required.
Very important step. So when you are given a question, you have to very clearly see what are all the parameters, how are they related, and then write all the relations which are related to those parameters. Correct?
All
Next step.
right. Then find the equation that relates the two given quantities.
Correct.
If necessary, eliminate one of the variables.
Perfect. Because if there are too many variables to work with, it becomes very
Mhm.
complicated question. So it is kind of necessary. And if you can eliminate, why not, right? If
All
not,
right.
then we will see implicit differentiation, which is going to be our next topic. If you're not able to eliminate one of the variables and we have to work with two variables, then we use implicit differentiation and we can still do it. Okay?
Mhm.
Yeah.
Okay. Apply chain rule to differentiate both sides with respect to time.
I
Solve
have
for
taken,
the.
yeah, sorry. I have taken time here because most of the time is the parameter which is changing, right? So
All
relate everything to time and then it becomes slightly simpler. Okay, so next point.
Because it is like rate of change. So
Rate of
rate,
change. Yes.
time, yeah.
Perfect. Perfect.
Solve for the unknown rate by substituting the results obtained,
Correct.
and then write solution including the units.
Yes. If you forget the units in your answer, you lose zero point
That's
0.5
the
marks, right? That's
no,
not done, right? At this stage, can't
no.
afford to do it. Right now. So we have examples and exam practice. Will actually apply the power rule, the chain rule. So that means you have to look into chain rule applications, and the questions are actually from previous test papers. So I'm calling it exam practice test. Okay. So let's look
Okay.
into the type of questions which we are going to solve today. So these are 5 questions, Amy, which we are going to solve. So think as if this is your test paper and you got these 5 questions. Read, understand, and then we'll discuss how are we going to solve them. Okay, start with question number 1, please.
A pebble dropped in a pond produces waves that spread at a constant rate of 1.5 meters per second. Find rate of increase of area of the circle when the radius is 10 meters.
Correct. So in this particular question, can you relate area with radius of a
Yeah.
circle? Sure, yeah. Area is pi r square, correct? So this is related a simple problem. We have area related with the radius and says find rate of increase of area of a circle when the radius is 10 meters. That means we are given the radius also, but the rate is given in terms of 1.5 meters per second. Per second means you have to differentiate with respect to time. Do you understand? Not
Oh,
with respect to radius. Got the idea?
yeah.
Parameter given to us is constant rate of 1.5 meters per second. Now we had a relation, area is pi r square. There is no time in it, correct?
Mhm.
Area equals to pi r square. There is no t in it. But both are changing with time. Since that pebble which dropped, it is spreading a wave. So the radius is increasing with time. And as the radius increases, the area is increasing with time. So both are
Oh,
functions of time, correct?
yeah.
So it is
That
like
makes
function of
sense.
a function. It's a chain rule. One affects the other with
Yeah.
time. Do you get the idea? So we are
Yeah.
going to differentiate both sides, area and radius part, I mean, left and right
Mhm.
side, with respect to time. And we already know dr dt, the rate of change of radius. Does it make sense now?
Yeah.
Okay, so keep that in mind and read the other questions, and then we will see how to solve them one by one. Yeah, question number
Okay.
2.
The volume of a spherical snowball of radius r is V equals 4/3 pi r cubed. A snowball is melting such that its radius is decreasing at the rate of 0.025 centimeter per second.
Mhm.
Find the rate of change of volume with respect to time when the radius is 2 centimeters.
Yes.
Question 3. The surface area of a sphere of radius r is expanding at the rate of 0.05 centimeter per second. Find the rate of change of area with respect to time when the area is pi centimeter squared. Question 4. Tap is filling water in a container at the rate of 240 centimeter cubed per second,
Yes.
and the level rises at a rate of 0.8 centimeters per second.
Correct.
So how fast is the volume changing for each centimeter increase in height?
Correct.
Okay. Question 5. Water is being pumped in the circular cone-shaped tank at the rate of 1.8 meter cubed per minute. This 5-meter height tank has a 6-meter diameter
At
at
the
the
top.
top. Find the rate at which the water level is rising when the water is 2 meters deep.
Perfect. So as you see in these examples, we began with circles, right? And we introduced to
Mhm.
you a sphere, and then we went on to a cylinder and a cone, correct? So
Mhm.
three-dimensional figures come in. So that is how most of the related rate problems are. We may have a two-dimensional problem, or we may involve 3D figures, right? And these are common shapes and very popular questions are these five which we are going to work on. So if you understand the concepts of solving these questions, then most of the test problems can be easily solved, correct? Now, we know the concept. We have to differentiate with respect to time on both the sides in most of the cases of rate of change. So let's review the concept of chain rule once again, right? So what I did in between is just to review what we learned earlier about the chain rule. So in chain rule, we know if I have a function f, which is also a function of g of x, and if I want to differentiate this particular function, uh, f of g of x, in that case, the derivative will be derivative of the outside function, right? Derivative of the outside function times the derivative of inside function, right? That is how it should be differentiated, correct? So what I did was, since earlier we were only differentiating with respect to x, so we always saw our equation like y equals to some function of x, correct?
Yeah.
Now it is not that case. Every time the parameters are changing, sometimes we are having volume, areas, things like that on the left side. On the right side could be height or radius or something else, correct? And the third parameter which comes in is time. We are differentiating with respect to time, correct? So there are many parameters to work with. So we have taken a very simple example, and that is consider y square equals to 2x cube. Very simple function I've taken, y square. Earlier we were putting only y equals to something, but I've kind of made it more complicated than that. Y square equals to 2x cube, where we are taking both x and y to be greater than or equal to 0, right? All positive values. In
Yeah.
real situations also, that's what you see, right? All those parameters are actually greater than or equal to 0.
Mm.
So, I mean, what you have to do here is first, part A, differentiate the equation with respect to x. That is what we had been doing all the time, correct? But the
Yeah.
same equation, we'll try to differentiate this equation with respect to y, and we will also differentiate the same equation with respect to t. So just to give an idea of how are we going to solve the word problems later on, let's just try with a simple function, which is y square equals to 2x cubed. And let's first differentiate with respect to x. So what happens? See, we have this function y square equals to 2x cubed. On both the sides, we are differentiating with respect to x, correct? So, but on the left side, we are differentiating y square with respect to x. We know that y is a function of x, kind of like this situation, right? Y is a function of x. We know that. So that
Yeah.
means chain rule will be applied, correct?
Oh.
So
Yeah.
derivative of y square is 2y, correct? Times the derivative of inside function, which is y. So it becomes dy dx. Do you see
Um.
that part? So
Yeah.
the derivative of y square now with respect to x is 2y dy dx as shown here. On the right side, it is exactly the same as you had been doing so far. So we are differentiating 2x cubed with respect to x. So 3 times 2 is 6, we get 6x squared, correct?
Mhm.
Because x is x, right?
Yeah.
No further going down into a chain, correct? The chain stops here at
Yeah.
x. Even if you do dx dx means 1, correct? Derivative of x
Yeah.
is 1, correct? Does it make sense?
Yeah.
Even if you write like this, which is like dy dx, you say, well, let me apply the chain rule. And so I'll get 6x squared dx dx. But dx dx is also 1,
One.
derivative of x is 1. Does it make sense? So it works
Yeah.
either way you may think about it, correct?
Mm-hmm.
So basically, we are applying the chain rule. Now, let's simplify it further. The question may be, find what is dy dx. So we can isolate. We can divide by 2y on the other side. So we get dy dx simplified form as 3x squared over y. Is that correct?
Mm-hmm.
So we'll leave it at this stage. Sometimes there may be problems where they will give you some initial values and they would like you to calculate what is dy dx. That could be a question, okay? Or sometimes they will like you to answer in terms of x. In that case, the y in denominator should be replaced by 2x cubed so that you could write an expression only in x.
Oh. Okay.
You could do that. But at present, we'll leave at this stage. There's a reason, because now we'll see what happens when I differentiate the same equation with respect to y this time, okay? So earlier we did differentiation with respect to x. Now we are differentiating with respect to y. So we'll do on both the sides of the same equation, y square equals to 2x cubed by dy of the function, which is y squared, correct?
Yeah.
dy of the same function on the right side is 2x cubed. Now, since you're differentiating with respect to y squared, derivative will be 2y, correct?
Mhm.
See, that is the end of the chain. We are differentiating with respect to y itself. So it is 2y.
Oh,
Got it?
yeah. Yeah.
On the other side, you know x is also a function of y. It's the either way, it's both ways, correct?
Mm.
Just as y is a function of x is also a function of y. So when we differentiate with respect to y, we get 6x squared dx dy. Got it?
Oh, okay. Yeah.
6x squared dx dy. Because you differentiated this time with respect to y, not x.
Mm.
So if you compare, do you see the difference? How it goes, right?
Yeah. It's
Correct?
like
Do you see?
switch.
So that's the tricky part. So in calculus,
Oh,
sometimes a lot of tricks are involved, and this is where most students get confused. So have a good look at it because we are going to solve most of the application questions using these techniques. Now it's kind of algebra. I'm just doing cross multiplication, writing it now not as dx dy, but as dy dx, flipping it over, right? Think as a cross multiplication type. Is that okay? So 6x squared divided by 2y comes on your right side, and I take this term on the left side as dy dx. Flip it. Got it?
mm. Mm.
So dy dx once again is 3x squared over y, exactly same as we got in the first case. We got the same result.
Oh.
You get the idea?
Wait,
Exactly.
we got the same result because they are interchangeable. Is that
Same,
why?
same equation. You do differentiation with respect to x or with respect to y or any other parameter.
Oh.
If you want, if you're interested in dy dx, you'll get the same result either way.
Oh, right.
Make sense?
Yeah. Yeah.
So that means it doesn't really matter. The only thing is,
Mm.
it really depends what you really want. Do you want
Mm.
dy dx or do you want dx dy? Accordingly, you could differentiate, right?
Yeah.
So what we did third time, we are differentiating with respect to time, t. We know both x and y are functions of time and they are differentiable for time. That is a restriction, okay? They should
Yeah.
be differentiable with respect to time. Only then you can differentiate, right? So we do d dt of y squared and d dt of 2x cubed. We know both are functions of time. So derivative of y squared will be 2y times the derivative of inside function dy dt. Chain rule. On the
Makes
other
sense.
side, 6x squared and derivative of inside function dx dt. Got it?
Yeah.
That is why we are getting that additional dx dt, dy dt. And
Oh.
when we do our derivatives now onwards, we'll get dv dt, dr dt, dh dt, right?
All right.
Those will be the parameters which are a function of time, but those are being differentiated. Is this point clear to you?
Yeah. Yeah.
Now, the related rate will be absolutely clear because, as in the last example we have seen, it is related to time. And when that is so, any parameter which is there, when you differentiate, you get a term like dy dt or dx dt or so on, correct?
Hmm.
So now let's begin and see how to solve the very first question, which is simplest of all. And to make it even simpler, what I've done is I've adopted two different methods of solving. Now, it may be convenient at times to adopt method number one and at times method number two. Sometimes both can be adopted. Sometimes if you forget one, you can use the other one. Correct? So it's kind of handy.
Mm. Yeah.
So once again, Amy, we have the same question, question number one, which is now an example since I'm providing you with the solution. But don't forget, at the end of these five examples, I've set up 10 questions for you. So I'm going to share with you 10 questions, which will be your test problems, and we'll discuss those later sometime, okay?
Okay.
Now, the very first one is, let's understand the concepts today. A pebble dropped in a pond produces waves that spread at a constant rate of 1.5 meters per second. As soon as you see per second, it gives you an idea. You have to differentiate with respect to time for sure.
Fine. Yeah.
Now the question is, find rate of increase of area dA of the circle when the radius is 10 meters. So increase in area, they are not saying with respect to what. Find the rate of increase of area of the circle when the radius is 10 meters. When radius is given to us as 10 meters, you have to find rate of change in area. So in general, rate of change means with respect to time. Does it make sense?
Oh,
Not
okay.
R. If you do with R, the whole answer will be wrong. Okay?
Oh, okay.
Very important. So first step,
Wait,
as we
so
discussed, yeah, yeah.
so if it says rate, we always just if it doesn't specify with respect to what, it's always time.
Yes, in one of our questions, we have specified with respect to height. You will see that question, right?
Yeah.
In one
Oh,
question, we have specified. But if it is not specified, and then you have to take time, and it is
oh,
given by
okay.
rate. It says that the constant rate is 1.5 meters per second. So rate here means with respect to time. Got it?
Yeah, makes sense.
It's implied. Now, clearly write down what is given and what you could get. So area, we know a relation which is pi r square, which is always given in your formula sheet. And then we are also given that the rate of change of radius is 1.5 meters per second. It's important to see the units. Sometimes they will say so many kilometers, right? And you might
Yeah.
have to change the units. And what you need to find is rate of change of area when radius is 10. So this is another way of writing. We dA dt with a line there and radius equals to 10. Perfect?
Oh, okay. Yeah.
Right. So that's the nomenclature. So we began with A equals to pi r squared, the formula, differentiated both sides with respect to time. So when you differentiate pi r squared with t, then you get 2 pi r dr dt, correct?
Wait, how do you get that again? Sorry.
Yes, the chain rule. So last part, you remember this part? When we differentiated y square with respect to time, we get 2y dy dt. When we differentiated
Mhm.
2x cube with respect to time, we get 6x square dx.
Oh,
Right?
yeah, yeah,
Same
yeah.
rule. We have to still differentiate the function x with time. We are not given that what is that relation between x and t, right?
Oh, okay.
But we are given the answer, which are saying, well, that rate is constant. It is 1.5 meters per second. You get the idea?
Yeah.
We are given the r dt is this. Otherwise, they may give you a relation. They may say, well, r is 1.5 t. Do you understand? Instead of
But how
writing
did
like this, they could say r is radius is increasing and the relation is r equals to 1.5 t. So when you differentiate dr dt, you get
oh,
1.5, correct? Derivative.
but what happens if you didn't know that the radius, like 1.5 meters? How do you know that the meter thing they're talking about is the radius? Why can't it just be like
Oh,
X?
because it is given in the question. It says a pebble dropped in the pond produces waves that spread at a constant rate of 1.5 meters per second, right? So when a circle is spreading, what spreads is the linear
Oh, the
thing is the radius only,
radius.
right? Does it make sense?
Oh,
Or
okay,
you can
yeah.
write radius as x, doesn't matter. You could do
Oh,
that.
okay.
So it is what variable you choose. So
That
since
makes sense.
radius they're talking about, and they are interested in finding rate of increase in area when the radius is 10 meters. So I'll take radius as my parameter. So that is why reading a question and understanding your parameters is very important, right? So coming
Yeah.
back to what is given to us is understanding what is given. We are given the relation, of course, area is pi r square and dr dt because I defined radius as r, correct? I should have written
Mm.
also let r be the radius, then dr dt is 1.5 meters per second. What we need to find is the rate of change of area when the radius is 10, which I have written in very short form, dA dt, that line means when r equals to 10. Clear?
Mm.
Okay. So you differentiate and now we get pi r squared to be differentiated with respect to time, outside function, 2 pi r, right? Chain rule, dr dt. You have to still differentiate r, which is a function of time, correct?
Mhm.
drdt. Well, you are given what is drdt, so which is 1.5. You are going to substitute that particular value,
Um,
right? Now, since we want what is DADT when R is 10, I replaced R with 10, and DRDT when R is 10 was also same because it is constant, it is going to remain the same, right?
mhm.
So at any radius, it is 1.5. So I substitute this particular value here, calculated my answer as 35, which is the exact value, and three significant figures, 94.2 meters per second. Okay?
Mhm.
Units are important. Area on the top, meter square, time, seconds. Got it?
Yep.
Okay. Now, we could have done it the other way, which is applying the chain rule. We know area is pi r square. The parameter is a and r. I could differentiate with respect to r also, right? Is that clear?
Yeah.
So I can say, what is dAdr for me? I didn't write that step. What is dAdr? I could here I've written here, right? So what is dAdr? dAdr is 2 pi r, correct?
Yeah.
A is pi r square. So if I differentiate with respect to r, not time, r,
Oh, yeah.
dAdr is 2 pi r, correct?
Yeah.
So what do you want? You want dA dt. So chain rule. dA dt is dA dr times dr dt. We just found that dA dr is 2 pi r, right? And dr
Yeah.
is 1.5. Got it? We got the same answer.
Yeah.
We got this.
So is it always like you know that layout that you have with the chain rule? I
Yeah.
know I learned the formula, but like when the parameters change, do you always have like whatever time is? So let's say you have the capital letter over time.
Yeah.
Would it always equal another capital letter over something else times that
Yeah.
over time?
Yeah. The chain will move like that. If there are only two parameters, then they kind of, you see, you can think about canceling
They
them.
cross.
dA dt, right?
Oh,
You
yeah.
can think like this.
Okay.
Not strictly, you cannot cancel, but this is how you can. It's like A is related with B, B is related with C. So that means A is also related with C, correct?
Oh, yeah, I didn't think about it like that.
Yeah,
Oh,
yeah. So
that's really, yeah.
if I add D here, then one more step will increase, kind of like that. Do you understand now?
Oh,
So
yeah,
the chain moves in this fashion.
yeah. I was just getting a bit confused on like
Yeah.
because I know the chain rule, but like it's when the parameters are all changing, so
Yes.
it's like which one goes where and stuff.
Yeah. So it's yeah. So when you put the next parameter, be careful. Think like as if it cancels and you get the final one. Correct.
Yeah,
So
yeah,
finally you want dA dt. So ultimately first and the last should remain. In between everything will cancel out.
makes sense.
If not, then you missed something in between. Right? Clear?
Right.
Okay. So second approach is very simple, and that is once you have all the relations, don't bother to mix them up, right? Just individually, A is related with R, dA, dr. Okay. R is related with height, dr, dh. You understand?
Oh, okay. Yeah.
Height is related with time, dh, dt. Now multiply all the three, cancel in between, and get your result.
Oh,
Got it?
yeah.
Got it?
So as the wording goes, you literally like as you're reading it, imagine those numbers like over each other. So if it says with respect, you literally write dr like that.
Yes,
So it
like
makes
that.
sense.
So if you
Oh,
put them together individually, also you can figure it out, multiply, and then get your result. You could do that. It's kind
yeah.
of saying like this, I mean, that let us say that the the gas prices are increasing and they have doubled, for example, right?
Hmm.
Because of that, the other factor could be delivery of the groceries, for example, right? So they want to incorporate that, then that will be, let us say, three times, right? So
Yeah.
ultimately, if you compare it from what was initial there and what finally product was, it will be two times, three, six times as expensive for the customers
Yeah.
because
Yeah.
there's a hike of twice and then thrice at the two intermediate levels, and ultimately what you get is six times. So this
Yeah.
chain rule, like it works in the normal way. You understand now?
Yeah,
Okay.
that makes sense.
So this was a very simple example, but an excellent example to understand the concept, right?
Yeah,
Let's
definitely.
take question number two. I like you to read it now and then explain me the two solutions.
Okay. So the volume of a spherical snowball of radius r is volume equals 4/3 pi r cubed. A snowball is melting such that its radius is decreasing at the rate of 0.025 centimeter per second.
Correct.
Find the rate of change of volume with respect to time when the radius is 2. Okay.
Clearly written this time. Yes, when the radius is
Yeah.
clearly written. But remember,
So,
in test papers, it is sometimes not mentioned,
yeah.
implied, right? So you have to think like, what?
Yeah,
What
like
am I
the first
doing?
question.
Yes.
Right.
So now,
So,
so see if that makes sense. What is given to you? Volume is given to us as 4 by 3 pi r cube. Rate
yeah.
of change of radius with time is given to us. Negative because it is decreasing. Do you understand? Going down,
Yeah.
it's decreasing. Negative 0.025 centimeters per second.
Oh,
Yes, centimeters. I wrote it meters here by mistake. It is centimeters. Okay. Okay, centimeters per second. And you need to find the volume, which is dv dt, at r equals to 2. Is that clear to you?
I
Okay.
like that layout.
Yeah,
This is nice and simple because, as it says, rate of change of volume, so that means dv, with respect to time over dt, and
yes,
then radius 2, line r equals 2.
perfect. This
That's,
is how
yeah,
you
it's
write
good.
it. Yeah. Many books follow this nomenclature, okay?
Oh,
So yes, this is a very standard way of writing. Sometimes they write when r, comma r equals to 2, but this is better. Okay.
yeah.
So you begin with, so we have two different approaches. One approach is just write the formula and we learn chain rules. So you can do inside function times the outside function times the inside function derivative, continue the chain, get the answer as we did first.
Yeah.
So dv dt is 4 by 3 pi r cube, three times. It gets multiplied, that 3 and 3 cancelled, right? So you get 4
4.
pi r square. Derivative of r is dr dt, correct?
Mm-hmm.
And then we know we need to figure out this volume change when r is 2. We can substitute the value of r. We also know what is dr dt. So we can directly do this and get our answer. Easy, right?
Would it be a negative though? Because it's
Yeah,
negative zero
yeah,
point
yeah, yeah. It's really negative. You're so right. So
zero.
this is negative. Yeah, this is negative. Correct. So negative, please. Good job. Negative. Now the second one is the method when we are given volume with respect to radius. Don't think much. Just find dvdr straight away, right?
Oh,
So
okay.
dvdr is 4 pi r square. So we get this term dvdr. We already know what is dr dt, right? We already
Yeah.
know what is dr dt. So when you multiply, you get dv dt. Does it make sense?
Yeah.
So, so actually, that is chain rule, right? That is what we had been doing. So again,
Mm.
I have to substitute this negative, which means negative, right? Negative, correct?
Do you think
Negative
that one's quicker? The second one?
is quicker. Yes, it's much quicker, and it is preferred method. So, as we move along, as the questions become very complicated, the second method is better. Because let's say something is changing along x-axis, along y-axis, and also along the z-axis. Is it okay?
Yeah.
I could say dx dt, dy dt, dz dt, all those terms separately, correct? And
Oh.
just just multiply them in one shot and get the answer. Okay?
Wait, if you did that example that you mentioned, if you did that with the method one,
Hmm.
would it be a bit really complicated? Because you got more
Slightly,
terms.
slightly, slightly.
Oh, okay.
Let's say we are
Okay.
talking about distances, then distance will involve that square root term and maybe a bigger thing. When it
Mm.
is two dimension, you got x square plus y square square root, right? x1 x1
Oh,
minus x2 whole square plus y1 minus y2 whole square. Then you
yeah.
have z1 minus z2 whole square and the square root and things like that. Right? It
Um,
could be more complicated, but anyway, uh, you have to do the same things. However, If you find this method simpler, it is good for you. Many
Okay.
students do not find it simpler. I mean,
Yeah, I didn't.
it is not easy to break down your problem into so many simple steps and connect them.
Hmm.
So
That's really hard. Yeah.
hard actually. So in that case, you have the formula, you know the chain rules, continue with the chain rule and get your result.
Oh, okay.
Correct?
Like I get the method.
Yeah.
It's just from the word problem and
Yes.
translating that into the DV over DR stuff.
Yes.
It makes sense here, but it's just that well, obviously when it gets more complicated, it's like, whoa, it's just too
Yes.
many parameters and things. Yeah.
Correct. Now, let me also give you one more point here. In this particular example, I forgot to write minus. That was my mistake. How? If I do without minus, correct, all this as
Mhm.
I did, but what I also did not do here is the last statement of writing down my answer clearly, right? Do you remember what I said in the beginning? In the beginning,
Write
I
your
was
solution.
saying that the last step is write solution including units, correct?
Oh.
So in my solution, which I kind of hurriedly wrote here, you know, I have not written my answer, right? I'm saying this is my answer, but I'm not writing it very clearly, correct? You have to write.
Oh.
When it says find rate of change of volume with respect to time when radius is 2, you have to write the rate of change of volume with respect to time is this with a
Oh, you have
negative
to write
sign,
like a statement.
like a statement.
Oh.
Or if you write, if you use all positive, that the volume is decreasing at this rate, then also it is correct because that decreasing takes care of the negative sign,
Oh, okay. Oh, yeah, yeah. That makes sense.
right? So,
Yeah.
so if you incorporate the word decreasing in your answer, then you're
You
not
don't need to
wrong.
put the negative.
Yeah,
Yeah.
then you're not wrong because you just took a rate of change and in your mind was decreasing, decreasing, decreasing. You put that, continue, right? You said decreasing, decreasing, decreasing in the answer, right? So normally in any calculations, we do not show units. It should be shown, but we don't, right? But at the
Mm.
end, we incorporate the units according, and if I incorporate the word decreasing, it will be okay. But okay, to begin with, we have to include minus and then work with negative. That is better. Correct?
Hmm.
Put minus here, but I forgot to put it there, right? Yes, when I did
Yeah.
calculation, I forgot. Yes. Okay. So it's important. Good note. Example number 3. The surface area of a sphere of radius r is expanding at the rate of 0.05 centimeter per second. Find the rate of change of area with respect to time when the area is pi centimeter square. Area formula is 4 pi r square. Okay, now you're given the formula. Area is 4 pi r square. You're also given the rate at which it is changing, 0.05 centimeters per second, correct?
Hmm.
Expanding means positive. And what you need to find here is rate of change of area with respect to time,
Time.
area when area is pi, right? So this time you are given when the area is pi. So not directly, you're not given directly the radius.
Mm.
You see
We
the
have to
difference?
find it. Yeah.
Find the radius. So when you read this question, first step should be to find the radius when the area is pi. Correct? So
Mm.
4 pi r square equals to pi, and then the radius is 0.05. Correct? So
Yeah.
basically, this particular thing is find dA dt when the radius is zero point 0.5. Is that clear to you?
Oh, okay. Yeah.
You can adopt either of these methods and get your solution. Is that clear to you?
Yeah.
So I'd like you to read this again and understand it, and then we'll move on to the next question.
So I read out loud or
Yes.
just in my head. Oh,
Okay, read out loud. Start from A equals to 4 pi r square.
okay. So first we write down what's given. So surface area is 4 pi r squared. We're given the rate. So rate, yeah, so that's 0.05 centimeters over per second. So derivative of r dr over dt, yeah.
Correct.
Then it says find the rate of change of area with respect to time. So we have dA over dt when area is pi. So that's why your A equals pi.
Yes.
But we need R.
Yes.
So to find that, you do pi equals 4 pi r squared. And
Correct.
then we can find R being R squared equals a quarter. And then square root that is a half.
Correct.
Yeah, so that makes sense. And then we're trying to find dA over dt.
Correct.
Oh, so we have to do so you do the derivative of the 4 pi r squared.
Yes.
Oh, okay, yeah, that makes sense. So you do 4 times 2 is 8 pi r, and then you have to do dr over dt. Yep, and we know what dr over dt is. That's the 0.05.
Correct.
So we just sub it in, and we found that the radius is a half as well. So you just sub that in as well, and you get that. Oh, okay.
Perfect. So you can adopt any of these methods and do it. Now let's move on to question number 4, which is tap is filling water in a container at the rate of 240 centimeter cube per second. The level rises at a rate of 0.8 centimeters per second. How fast is the volume changing for each centimeter increase in height? You see that? How fast is the volume changing for each centimeter increase in height? What does that mean? What do you have to find?
The dv over dr.
H.
Oh, H. Yeah, sorry. Why did I say R? I meant H.
You get
So
the
it's
idea?
height. Yeah.
You have to read your question properly, understand what is required, right? It's very tricky. All of a sudden, they are just changing the topic and getting some new parameter, right? That's what happens in examination. You began the dy dx, dy dx, dy dx. All of a sudden, dy dt, dy dt, dy dt. And then the question is dy dh.
Oh.
So it's a kind of a difficult thing sometimes to switch. So
Yeah,
get
yeah.
this, okay? That's why I took these 5 examples. They have a lot of variation and you learn with each example. Perfect? So read the question once again, and I have used the second way of doing it. Explain me why in this case I have used the second case, not the first case. Okay.
Okay.
Yeah, read the question, then we'll understand how you see this one. Think as if it is part of your book, right? You're just reading the
Okay.
example from the book. Do you understand it? That's the question for me, right?
Right.
Okay.
So tap is filling water in a container at the rate of 240 centimeter cubed per second, and the level rises at a rate of 0.8 centimeter per second. How fast is the volume changing for each centimeter increase in height?
Correct.
Okay, so I would start by writing, so we're given the rate, but because it says centimeter cubed, I know it's going to be volume over time. So dv over dt equals 240 centimeter cubed per second.
Perfect.
Okay, and then I would write, so I'll write the question, what they're asking. So how fast is the volume changing for each centimeter increase in height? So I'll write dv over dh,
Yes.
and then that's question mark because we need to find that.
Correct. In between.
That's the middle part. Yeah, the level rises at a rate of 0.8 centimeter per second. So I know it's something over time.
Height. Level is height.
But it has to be height. Oh, okay. Okay.
So
see, what I would have done, I would have put that something like X, and now I have like 4 variables, and I'm like, oh no. Yes. Or like 3. Yeah, okay.
Correct. So since we refer to height and since level rises, so it means level is height.
Oh, yeah.
Getting my point? Well, many cases you have to draw a figure, right? So whatever could be the figure, you have to draw a figure here. So once you draw a figure, things become clear. So we'll get into, it was not mentioned what kind of container, so we didn't get into that complexity. And, figure is not really helping us much in this particular case. Perfect?
Yeah.
Okay. Now, so when you come to the stage and the level rises at this rate, and when you end up with height, then you can correlate that the level is the height level they're talking about, right?
Oh, okay.
So initially, when you're given, you could also define here, let the height be h and all those things, volume be v.
Yeah, I think that would help me. Yeah.
That should help you. First, you write down that, right? And then you write down what I have written. It's better to define the variables first. Now, in this particular case, we want to relate dv dt by dh dt itself, correct? So that means we should be applying the chain rule. dv dt is dv dh times dh dt. So in that, we have our answer, right? Do you see one part?
Yeah. So you just sub it.
Yeah. So if I sub this, we know that, and then dv dt we are given. I mean, let me put those two orange which are given to us. This is given, right?
Mm-hmm.
And the answer is hidden, which is right there, dv dh.
Yeah.
Do you see that part? So it's not a difficult question. Actually speaking, it gives you everything. It's just rearranging those terms.
Yeah. Yeah.
Got it?
Yeah. Would there be questions where they don't give, so they will only give two of them, and they're not even asking to find one of the middle ones?
They can give you an expression. They could do many things here. They can tell you what type of container it is. If you know the type of container, for example, if it is a cylinder, then radius and height will change at the same rate. If it is a cone, right, it all depends. It depends, right? So we'll get into an example how they are going to change, right? You see, if it is something like this, they are going to change at the same rate. Do you see that?
Yeah.
Height and the radius, right? It's kind of a linear relation, but not here. Initially, it is very, very fast. The height changes faster, right? It's kind of much, much faster, and then it decreases. This is a differentiation. And the shape could be, sometimes like this, correct? So depending on the shape, we know how this thing is going to work out. So they might give you a shape, they might give you a relation, then you can figure it out, right? In our case, we have given you the value. Easy to work with, because these are like getting started with rate of change examples. You get the idea, right?
Yeah, that makes sense.
Give you all the three things, and now explain me the solution which is right there before you.
So we start off by, I would actually start off by just defining the variables.
Yes.
So I read it, and like I said before, when we see centimeter cubed over second, we know volume is involved, and per second means it's over time. So dv over dt equals 240. And then it says level rises at the rate of 0.8 centimeter per second. So because it says level, and in the question it says increase in height, we have to make that connection between level and height. So the level is the height. Yeah. So that means 0.8 equals d h over dt, because it's per second. And then it says how fast is the volume changing for each centimeter increase in height. So that means it's dv over dh. Perfect. So to show the relation between them, we use the chain rule, because it's much easier to use a chain rule, as you can just sub the values in, because we've already found two of them. So dv over dt equals dv over dh times dh over dt. And we know that because if you get confused which way around it is, just think of cross multiplying those, they cancel. So it is that way. And then we've already found dv over dt, which is 240. So you just sub that in. And we found dh over dt, which is 0.8, sub that in. And to find dv over dh, you divide, like normal equation, you just do 240 divided by 0.8, and we get 300 centimeter cubed, because it's volume, per second.
Sorry, dear. Not
you have to write the statement.
Centimeter. Oh my God. Another mistake.
Oh yeah, because it's in height. Oh.
Centimeter. So actually I did them today, only all these questions, so that we could have this lesson. And hurriedly I see there are a lot of mistakes which are still there. But I hope now it makes sense, right? So you have
Yeah.
to be careful. dV over dH. So this unit will be centimeter cube over centimeters, correct?
Mm.
And
And no,
now,
actually, I know that was a mistake, but it was actually good to see because that would be something that I would have done in the exam, you know?
okay.
Because I'm thinking it's always over time, but now
Yes.
I'm looking at the units. Yeah,
Yes.
it's very important actually.
And don't cancel centimeter cube by centimeter, right? As
And put the
centimeter
centimeter
square.
squared.
That will be wrong, absolutely wrong. Okay.
Okay.
So, so these are good things to learn as we move around.
Yeah,
Hurriedly, we do a lot of mistakes, as I've done so many times. Okay.
especially under conditions.
Perfect. So you have to be very careful when you do. Question number 5 for you now. This is where we have not given you directly the relation, but you have to derive the formula. Is it okay?
All
So
right.
please once again read example 5, and then we'll look into the solution.
Water is being pumped in the circular cone-shaped tank at the rate of 1.8 meter cubed per minute. This 5-meter high tank has a 6-meter diameter at the top. Find the rate at which the water level is rising when the water is 2 meters deep.
Do you understand the question?
So I think I'll just start by stating a few things.
Yeah, sure.
So it says 1.8 meter cubed per minute. So we know that's meter cubed, so that's with volume. So I'll write dV per minute being time over dt equals 1.8 meter cubed per
Minute.
minute. Yeah.
Yeah, okay.
Then I write down, because we're dealing with volume,
Yes,
I would write down the volume of a cone. So a third pi r squared h.
correct.
And it says find the rate at which the water level is rising. The water level is rising when the water is 2 meters deep. So because it's so here it hasn't stated with respect to what, but because it says find the rate, we know it's with respect to time.
Correct.
And like in the previous question, it says the water level, so we know the level, they're dealing with the height. So
Yes.
dH over dt, and it's saying the height is 2 meters.
Correct.
So that's everything from the question.
Perfect.
Now to solve it.
Okay. In the question, we have also given this parameters for the cone, right? So right circular cone. A cone could be placed either way. It could be upside down also, right? The way I've shown, it could be the other way also. However, the question says this 5-meter high tank, so 5-meter high tank, correct,
Mhm.
has 6-meter diameter at the top. So bigger surface on the top. Do you understand? So
Yeah.
normally you'll think a stable structure should bigger thing diameter should be on the bottom,
Yeah.
like a cone upside down, right? Well, the question is saying like this, you can't change it, right?
All right.
So we know this diameter is 6, so the radius I've written as 3, correct? Did-
Mm-hmm.
right? Height I've shown here. So instead of showing a 3D figure, I've taken a cross section of the cone, which is always a triangle. So in a triangle, we can relate height with radius. There are two different parameters, right? So we can
Mm-hmm.
relate height with radius using similar triangles. So this bigger triangle is similar to the smaller triangle. So the ratio of their corresponding sides is a constant. So
Mm-hmm.
from there, we begin our solution, correct? So important point here is to relate R with H to write volume in a single variable, right? And we are using similar triangles to relate them. Since we
Wait,
know,
why can't,
yeah,
sorry,
yeah.
why can't you relate H with R? Why does it have to be R with H?
Either way, either way.
Oh, okay.
Either way you could do it, but see what is given to us, right? So, and what we need to find. We want to find something when H is 2. So we want to
Mm.
keep H and get rid of R. In the expression,
Um,
we are always working with dH, dt when H is 2. So we want to find what is happening when height is 2.
oh, so you can't get rid of H.
Yeah, you should not get rid
Oh,
of H.
right.
You have to get rid of R.
That
Okay?
makes sense. Yeah.
Yes. So now from the ratio, we know this R over H is same as 3 over 5. Does it make sense, right?
Mhm.
So we have R over H as 3 over 5. So R is 3 over 5H. So in the formula, wherever R was there, that has been replaced by 3 over 5h. So rewrite your formula in one variable. That is your first step. So now the volume is 3 pi over 25 h cube. Got that part?
Mm-hmm.
This is your first major step. And most of the questions will actually be like this, right? So
Oh.
they will not straight away give you the values that this is the rate at which it is doing this. You may have to relate them. Perfect. So we
Mm-hmm.
related. Now you apply the techniques which we had been applying so far. Clear? The chain rule.
Yeah.
So we know dv/dt. So we have a formula here. So dv/dt is d dt of the whole thing. So differentiate with respect to time. Multiply by 3h square, we get this part, and then dh dt, correct?
Yeah.
You need to find dh dt, so isolate dh dt. Put all other things on the left other side. Is it okay?
Yeah.
And now substitute h equals to 2 in your expression. You know what dv dt is and get your answer. And then,
Um,
good, I wrote the answer for the first time in a statement. The water level is rising at the rate of zero point 0.4 meters per minute. Clear?
mm-hmm.
So that is how you're going to solve it. Is it making sense now?
Yeah. All right.
Okay.
It's not that bad.
It's not that. So finally, you have understood clearly how we are going to
Yeah.
solve these questions. Can you summarize this, please, for me?
Yeah. Right. So when we see a problem like this, um, I obviously find it a bit helpful if we start by defining the variables. Read the question, like before you even attempt to start the question, just read it, see what the values are. If we see meter cubed over second, immediately write like dv over dt equals that. Write down all your points, and then whenever these are just a few like key points. When you find the question and you get your answer, always make sure you write the statement at the bottom, clearly stating the rate of changes, and then write your answer. We can apply the chain rule,
Yes.
and the extended
Power rule.
power rule, extended power rule.
Correct.
So both of them are really good. The chain rule is quicker,
Yes.
but if you want to understand it really well, I recommend the power rule for beginning with this chapter, because it's actually really good. And when it comes, oh yeah, so make sure units, that's like key thing. When it's, so if it says like, let's say we have to find dv over dt, you have to make sure you have centimeter cubed per seconds. And if it was centimeter cubed over centimeter, don't cancel that out and make it centimeters squared if the question's asking for volume. So don't do that, because these are like, even though they're just 0.5 marks, they all add up, and then
All right.
eventually it's like you lost like so many marks for silly mistakes like units and things. And I think that's it.
Good. So now you've understood everything, Emmy. I just introduced you to 5 examples. That should be a good base for you to solve many questions related. So now I'll share with you your test paper, kind of practice test paper. So let me see. We have, there we go. So here is a playlist for you, Emmy, which is called Related Rates of Change, right? For
Mm-hmm.
GCSE, IBSL, many IB students are also doing the same thing. And the curriculum here has a code word of MCV. So they also follow the same pattern and same things, right? So for them, I have a very special playlist, which is related rates of change. The very first question here has 10 questions, right? So let's begin. I'll just share with you these 10 questions. So these are the questions for you. As you can see, all are related rate of change questions. So I'll actually forward you the link. So you have to copy these questions, all 10 of them. These are the first 5. Then you move on. And you do have solutions for all the 10 questions also. And these are the rest. Okay. So
Yeah.
these are 10 questions for you. You should write all of them and try to solve them. And what you can do
Okay.
is once you solve them, if you have any difficulty, you can go through the video, understand the concept. We are beginning with very simple questions as we began in the examples so that you understand the concept and then build on the foundation and solve some difficult questions later on. Correct?
Yeah.
So, so by the and you should be in a position to do all the 10 questions. Here, for example, question number 8 has got some rate of change with in dx and dy, so two different directions. So we have all types of examples here, which are from test papers. That's kind of important. You'll also see in the playlist that there are many, many more videos. There are 9 videos in this which cover different aspects of rate of change, right? So we're looking at related rate of change, we're looking at rate of change, and sometimes we're focusing only on velocity, acceleration, and displacement, right? So that is also a rate of change application. Huge, right? So, and many times we also only figure out with the graphs, right? So we only work with the graph. The graph is given to you, and uh, let's skip this ad. Okay. So you are given a graph, and from the graph, you have to answer rate of change questions. Does make sense?
Mm.
So, so the rate of change is such an important unit for you. You have to do it in many different ways. Sometimes
Uh,
we are also having rate of change when a situation is kind of similar, but different cases are being considered. For example, this particular example, which I'm now sharing with you, has a case where you have rate of change of a shadow. Now, rate of change of a shadow example could be how fast is the shadow length changing, or how fast is the head of the shadow changing. So different parts will give you different kind of a result, right? So
all right.
understanding the question very clearly is kind of key in answering rate of change questions. So I'll request you to at least answer the first 10 questions and then check the other videos to see the variety which you could expect in examination. Is that clear, Amy?
Yeah.
So make a note of this particular playlist and follow it. If there is any difficulty, post your questions and then we'll discuss that. Perfect.
Okay. Yeah.
So that is how we are going to work with. And with this, our unit on rate of change is completed. We'll now take up implicit differentiation next time. Is that okay?
Okay. Yeah.
Great.
Just a quick question. What's the difference between related rate of change and just rate of change?
Okay. In very good question, actually. When I say rate of change, I'm not relating it to something else. These examples which we did today, it was related because we are saying when volume is increasing, the radius is increasing. Find the rate of change of volume with respect to radius. You're getting my point? How we related the two?
Yeah.
When the radius is increasing, the area is increasing. So we have to relate area with radius and then find.
Radius.
So we have always involved at least two parameters. So when we say
Oh,
related rate
okay.
of change, in that case, two things are involved. But when we simply say rate of change, it is dx dt, dx dy, what you have
Oh,
gradient. So you can say rate of change is gradient. Is that okay?
yeah, yeah, yeah.
So all the
Oh,
examples with applications where real sense you're only finding gradient, a tangent slope, that is rate of change, but applied
oh,
into a situation. So it's a real life
hmm.
situation. So we say rate of change example. Is that clear to you now?
Yeah, that makes sense. I was
So
just wondering.
so these are the two different. So we did examples based on rate of change earlier, and most of the
Mhm.
time we referred to gradient, and that was rate of change. Clear?
Oh, okay. Yeah.
So,
Yeah.
that's where we end the lecture today. And all the best with the questions, and feel free to share the questions and their difficulties if you have any.
Cool. Thank you so much, sir.
Bye.
I really appreciate it.
Okay, thank
Thank
you.
you. Bye.